Okay, with problems 8 and 9, we want to find the derivative of an integral defined function. And I'm going to show this two ways. We'll first talk about where this idea, or what this idea relates to. This comes back to the fundamental theorem of calculus. That should be a dx. So we have the derivative of an integral defined function from some constant to x of f of t dt. That derivative is simply f of x, which means all we're going to do is take the integrand, that f of t, and replace the t with that upper limit of integration to get f of x. That's what the fundamental theorem of calculus says. Now, when that upper limit is not just x, but it's a function of x, then in addition to substituting that function of x for t in the integrand, we're also going to have to multiply by its derivative. So this is a chain rule, in a sense, when you have a function of x instead of x as the upper limit of integration there. So in a very simple way, this problem becomes the derivative of the integral from 1 to the square root of x of 14 t to the 5th dt is just going to be 14 instead of t, square root of x to the 5th. Then we have to multiply that by the derivative times the derivative of the square root of x, which we can also write as x to the 1/2, and we'd be done. So 14 x to the 1/2 raised to the 5th power, and the derivative of x to the 1/2 is going to be x 1/2 x to the negative 1/2. Now 14x to the 1/2 raised to the 5th power is 14x to the 5/2, and that's going to be multiplied by 1/2 x to the negative 1/2, and 14 times 1/2 is going to be 7 x to the 5/2 times x to the negative 1/2. We multiply two numbers with the same base, we add exponents, so 5/2 plus negative 1/2 is 4/2, which is 2, 7x squared. So the answer here is B, and it's not too complicated. All we're doing is substituting the upper limit for t and then multiplying the result of that integrand by the derivative of the square root of x. Now I want to show this in a slightly different way, hopefully to illustrate. It's going to take a little bit more time, and you'll see why we come up with the same answer, so we might as well just use the shortcut. So first of all, I'm going to start with, now this only works because of 14t to the 5th is integrable. We can find the antiderivative of it, and that's going to be 14t to the 6th over 6. Well, let's just write it out first. 14t to the 5th dt. So that would be 14 over 6 t to the 6th from 1 to the square root of x. And so 14 over 6, top and bottom can be divided by 2. We'll get 7 over 3. Then we're going to evaluate t to the 6th at the upper limit. So that's x to the 1/2 raised to the 6th power, then minus 1 to the 6th power. So we end up with 7/3. X to the 1/2 to the 6th is x to the 3rd minus 1. Alright, so, and if we want to write that out, 7/3 x to the third minus 7/3. So this is what the first part of this is asking us to do. Find the integral from 1 to the square root of x of 14t to the 50t. And that's what we did. But we're not stopping there. What we really want to do is to find the derivative of that. So let me go ahead and take the derivative with respect to x of 7/3 x to the third minus 7/3. And so what happens here, we are going to bring down the 3, multiply it by 7/3. So 3 times 7/3. Now reduce the exponent, and the derivative of negative 7/3 is just 0. So 3's cancel, and we end up with 7x squared, which is the same answer that we had using the other method. Now, you might ask, why don't we do that all the time? Well, first of all, we can't always find the antiderivative of the integrand. And if we can't, then it's much simpler to just substitute the upper limit of integration for t, simplify the expression, and multiply it by the derivative of the upper limit. So usually it's a fairly simple process. In this case, it's hard to tell whether the first method or the second method was faster, but the first method usually is much faster. So, and the second method doesn't always work if we can't find an antiderivative of the function. But you can see how this whole process played out there. All right, we'll stop this video here.